In this video, we'll study the motors used for electric traction. Let us see the motors for electric traction. Series and compound motors, they are employed on DC traction system, whereas single phase series motors and three phase induction motors they are employed on AC systems. The service conditions for these are extremely severe. Therefore, the motors should have very robust design and they should be of totally enclosed type so that they can protect themselves from water, sleet, etc. Let us see the different characteristics of DC motors. The first one is torque current characteristic. So for a DC motor, the supply voltage equals the sum of back EMF and the drop in the armature. That is E equal to EB plus IaRa, where E is the supply voltage, EB is the back EMF and IaRa is the drop in the armature. Multiplying by the term EA will give us the equation EIA equal to EBIA plus IA square RA. The term EIA here is the power input to the armature. And EBIA therefore gives the electrical power converted into mechanical power at the motor shaft. If T is the torque of the motor in Newton meter and N is the speed in RPM, then the power developed is given by 2 pi NT by 60 watts. This power developed is equal to EBIA, the electrical power developed. Therefore, we get the equation for torque as 60 by 2 pi into EBIA by N, that is equal to 9.55 into EBIA by N. But we have the equation for EB, that is P5 NZ by 60A, where phi is the flux per pole in Webers. P is the number of poles. N is the number of rotation in RPM. Z is the number of armature conductors. And A is the number of circuits in the armature winding. Therefore, we can get the equation for T as T equal to 9.55 into P5 NZ by 60A into IA by N Newton meter, which is equal to 9.55 P5Z by 60 into IA by A, which is equal to 0.15925 into Z of IA by A into P. So this is written as 0.1592 into flux per pole, that is 5, into armature ampere conductors, that is ZIA by A, into number of poles, that is P. The shape of the torque armature current curve is shown in the next slide. So the torque armature current curve is as shown in the figure. So it is drawn for both shunt motor as well as series motor. So the torque, it is proportional to Ia into phi. So in case of shunt motor, phi is constant. Therefore, the torque varies with Ia. So for shunt motor, flux phi remains constant if supply voltage is constant, which means that torque varies with armature current, giving the torque current curve of the shunt motor as a straight line as shown in the figure. Coming to series motor, the current passing through the armature excites the field. Therefore, phi is proportional to Ia. Hence, torque is proportional to Ia square up to the limit of saturation. So, the torque current curve is in the shape of parabola up to the saturation level. Beyond the saturation level, the torque is proportional to Ia only, and hence the curve becomes a straight line as shown in the figure in the dotted section. Next we will see the speed current and speed torque curves. So for a DC motor, we have the equation of Na as N equal to E minus IaRa into 60A by P phi Z. This is got from the equation of Eb, that is P phi Nz by 60A, and substituting for Eb from the equation of E, that is E equal to Eb plus IaRa. So we can conclude that N is proportional to E minus IaRa by phi, since the number of poles P is constant, number of armature conductors Z is constant, and number of circuits in the armature winding A is constant. Therefore, we can get the expression reduced to N is inversely proportional to phi. Now we have the equation of T, that is 9.55 P phi ZIa by 60A. So getting the ratio of T by Ia, we get it as 9.55 P phi Z by 60A. So we have the equation written as 9.55 Ia by T as 60A by P phi Z. Substituting the value in the equation of N, we get N equal to E minus IaRa into 9.55 Ia by T, that is equal to 9.55 E minus IaRa by T by Ia. So the speed current and speed torque curve is as shown in the figure below. So speed torque curve, it is a straight line for shunt motor, whereas for series motor it is as shown in the figure. Similarly, the speed current curve, that is the armature current. So the curve is straight line again for shunt motor, and for series motor it is as shown in the figure. So the series motor, it is ideally suited for traction since it is capable of exerting a high starting torque and it possesses high free running speed, and the speed decreases as the torque increases, thereby protecting the motor against overloads. Next topic is series and shunt motors for traction services. So in that we have the first operation, that is parallel operation of series motors with unequal wheel diameters. So considering the two motors A and B which are identical, their speed current curve is as shown in the figure. So speed versus armature current. So we have the curve as shown. So consider two identical series motors having the speed time curve as shown in the figure. Suppose the motor A drives a wheel of 91.5 centimeter diameter and motor B drives a wheel of diameter 88.9 centimeter. So for a given speed of the car, the speed of rotation of motor B will be 91.5 by 88.9, that is 1.03 times that of speed of A. That is NB, the motor B speed, is equal to 1.03 times NA, the motor A speed. So when the motors are in parallel, the current input to each will be given by the corresponding points on the speed time curve B and A for motor B and motor A. So looking at the figure, we can see that the division of load is there, and it is seen that there is not much difference between the current drawn by the two motors, that is IA and IB is nearly equal. So we can conclude that the motors are fairly equally loaded. So the division of load, though it is there between the two motors, but seeing the speed time curve, there is not much difference between the current drawn by the two motors. Therefore, we can conclude that the two motors are fairly equally loaded. Next one is series operation of series motors with unequal wheel diameters. So we have the circuit. So the circuit for the series operation of series motor is as shown. So the two motors, they are identical, having equal resistance R. Since they are connected in series, same current flows through the two motors. But due to the unequal wheel diameters, they deliver different loads and hence the voltage across the two motors is different. That is, VA and VB is not equal. So we have the speed proportional to V minus IR and V equal to VA plus VB. So we can get the ratio of speed for the two motors NA by NB as VA minus IR by VB minus IR. So VA minus IR is equal to NA by NB into VB minus IR, that is equal to NA by NB into V minus VA minus IR. Therefore, VA is NA by NB into V minus IR plus IR minus NA by NB into VA. Therefore, VA into 1 plus NA by NB is equal to NA by NB into V minus IR plus IR, which implies the voltage across motor A, VA is NA by NB into V minus IR plus IR divided by 1 plus NA by NB. Similarly, we can get the expression for VB as VB equal to NB by NA into V minus IR plus IR divided by 1 plus NB by NA. Next, we have parallel operation of shunt motors with unequal wheel diameters. So we have the speed, armature current curve plotted for the shunt motors in parallel operation. So looking at the speed current characteristic, we can see that for a small difference in speed of the two motors, there is large difference in the current, which means that the two motors are loaded unequally. This is due to the flat speed current curve. Next is series operation of shunt motors with unequal wheel diameters. So the circuit of series operation of shunt motors is as shown in the figure. This case is similar to that of series operation of series motors, and the same equation of VA and VB holds good. Next is compound motors in parallel with unequal wheel diameters. So we have the speed current curve, which is again a steep curve. So for cumulatively compounded motors, the speed current curve is steeper than that of the shunt motor, and hence we can see the loading is not equal for the two motors. There is unequal loading between the two motors. Therefore, we can conclude that if shunt motors or motors with shunt characteristic are used for traction, then slight inequality in the wheel diameter will cause large variation in the load division. Next topic is two similar motors of series type used to drive a motor car. This is explained by the following example. The supply fed to the series connection is 650 volts. If the first motor is geared to the driving wheel of radius 45 cm and the second motor to 43 cm, and if speed of first motor when connected in parallel to the second motor across the main supply is 400 rpm, determine the speed of motors when connected in series. Assume the armature current to remain same and armature voltage drop of 10% at this current. We have N is proportional to V minus IR by phi. Since the current through the motors in series connection and in parallel connection is constant, the flux phi remains constant. Therefore, N is proportional to V minus IR. For the series connection of series motors, V equal to VA plus VB. Therefore, NA is equal to VA minus IR and NB is equal to VB minus IR. Since the motors are similar, the resistance RA is equal to RB is equal to R. The ratio NA by NB is VA minus IR by VB minus IR. Let it be equated to a constant value rho. Therefore, VA minus IR by VB minus IR is equal to rho. So, VA minus IR is equal to rho into VB minus IR, which is equal to rho into V minus VA minus IR. So, VA into 1 plus rho is equal to rho into V minus IR plus IR. So, VA is equal to rho into V minus IR plus IR by 1 plus rho. Similarly, VB is equal to 1 by rho into V minus IR plus IR by 1 plus 1 by rho. Also, we have NA by NB is equal to RB by RA, where R indicates the radius of the corresponding driving wheel. Therefore, NA by NB is equal to 43 by 45, which is equal to rho. Therefore, VA is equal to 43 by 45 into 650 minus 65 plus 65 divided by 1 plus 43 by 45. So, the armature voltage drop, it is 10% of supply. Therefore, IR is equal to 10% of 650 volts, which is 65. Therefore, we get the value of VA as around 319 volts. Therefore, we can calculate VB is equal to V minus VA, that is 650 minus 319, which is 331 volts. The speed of the motor A is 400 RPM, that in parallel connection. that is at a voltage of 650 volts. Therefore, let Na be 400 rpm and let Na dash be the speed of the motor A when it is connected in series with motor B. This is at 319 volts. Therefore, we have Na dash by Na is equal to 319 minus IR by 650 minus IR. Therefore, we get Na dash is equal to approximate 175 rpm. Also, we have Na by Nb equal to 43 by 45, which is also equal to Na dash by Nb dash. Therefore, we can calculate speed of the motor B in series connection. Nb dash equal to 45 by 43 into Na dash, that is approximate to 184 rpm. Next topic is tractive effort and horsepower. So in case of DC series motor, flux is proportional to current. Therefore, we have speed N is proportional to V by phi. Since phi is proportional to I, we have N is proportional to V by I, or speed is proportional to 1 by I when V is constant at 1 per unit. And torque, we have T is proportional to phi I, and since phi is proportional to I, we have torque proportional to I square, which implies I is proportional to square root of T, which implies N is proportional to 1 by square root of T. Therefore, the horsepower HP is given by HP is proportional to T into N, which is proportional to T into 1 by root T. So HP is proportional to root T. So the power taken from the supply is proportional to the square root of torque. This equation holds good for the AC series motor also. Coming to DC shunt motor or three-phase induction motor, the speed is fairly constant. Therefore, HP is proportional to Tn. It is proportional to T since speed is constant. So the power taken from the supply, it is directly proportional to torque. This shows that the amount of power required in case of DC shunt motor or induction motors is more compared to the power required in case of series motors. The series motors, they make an ideal choice for the traction service since it gives a high starting torque. It has high free running speed. So the speed of the motor is high during the free running period in the speed time curve due to the armature current being low. Next, we have the speed automatically decreases as the torque increases, and for the same torque, power and current drawn from the supply is more in case of shunt motor compared to series motor. Problem statement: a locomotive exerts a tractive effort of 33,800 Newton in hauling a train at 48.3 km per hour on the level track. It has to haul the same train at the same speed on a gradient, and the tractive effort required is 53,400 Newton. Find the power delivered in HP by the locomotive when the motors used are DC series motor or induction motor. So we have the power delivered in HP on level track given by FT V into 1000 by 3600 into 746. This equation is drawn from the power output at the driving axles. So substituting the values, we get the expression turned into 33,800 into 48.3 into 1000 by 3600 into 746. We get it around 608. Next, we have to find the HP required when the motor used is DC series motor. So for DC series motor, horsepower is proportional to square root of T. Therefore, the power required is equal to the power on level track into square root of Ft required by Ft on a level track. So we get the value around 764. So since Ft is also given by the equation 2 neta T gamma by D, we have substituted in place of T the tractive effort value. Similarly, for induction motor, we have power HP proportional to T. Therefore, HP required is equal to 608 into the tractive effort required by tractive effort on a level track. We get it approximate to 960.